Okay, everybody is welcome to our mathematics and applied mathematics research lecture series on n-ary algebras and Hom-algebras by our researcher Abdennour Kitouni. He will continue with the second lecture in the series today, and it will be about it will be about n-ary algebras and some general properties and some more examples, I guess. As I told before, everybody should keep microphones muted and ask questions after the lecture, since we are recording that. Abdennour, so it's your time.
Yes, thank you and welcome everyone. So today we are going to talk about some more general properties of n-ary algebras. Today's lecture is going to be more technical and less less like the last one, so to say. So the outline of this lecture is the following. I'm going to be addressing three points. First, present the construction of how factor algebra looks in the n-ary case, then modules over n-ary algebras, and the structure constants and how we work with them. So let me begin then with factor algebra. So first I shall recall what an ideal is. So if we take an n-ary algebra and a linear subspace of A, then we say that it is an ideal if and only if all multiplications with one element of S and n-1 arbitrary elements of A in any order, so S in first, second, or whatever position, all of these should belong to S. And if the algebra we began with is symmetric or skew symmetric, then it is sufficient to have only one of these in S, we say this one. And now that we are going to work with factor algebras, you will see that this this definition is relevant actually. So we take an n-ary algebra and then an ideal of A, and on the quotient vector space we define the operation that I will denote Mbar here. That is Mbar of n equivalence classes So I was saying M of n equivalence classes is M of their representative plus I. So now what I need to prove now is that this definition makes sense, that this Mbar is well defined. Of course, another thing before we move on, this factor algebra or quotient algebra will be always of the same type of the original one as those total associativity, skew symmetry, Jacobi identity, and all of this kind of properties are transmitted naturally to the quotient. So let's begin. We take n elements x1 to xn and then x1 prime to xn prime, so that each one of these one is equivalent to its correspondent. Xk is equivalent to xk prime. That is xk minus xk prime is an element of I. And we start with this Mbar of x1 plus I to xn plus I is equal to this. And then what we do is we add and remove x, or add and subtract x prime n in the last entry. And after moving elements around, we end up with xn prime plus this, which is, as we said before, an element of I, using multilinearity here. And then this xn minus xn prime is an element of I. And then since I is an ideal, then this m of this is also an element of I. And then we end up with this. We changed one element here with another representative of the same equivalent class, and the result is still the same. Then we do again the same process on x n minus 1. And we end up with this xn minus 1 prime, xn prime. And then we continue the same with the same thing over and over until the last element. So we get this, that m of x1 xn plus I does not depend on the choice of representatives in the equivalence classes we have. So at each one of these steps, we apply we use one of these. So that's why it's important to have them all. So a few other properties also related to the ideals and the factor algebra is that if I take a family of ideals of A, then their intersection and their sum is also an ideal of A. Also, the image of an algebra morphism is a subalgebra of B, and the kernel of the algebra morphism is an ideal of A. And then we have the well-known isomorphism theorem that extends naturally to the case of n-ary algebras. So if you take two n-ary algebras and a homomorphism between them, then A factored by the kernel of F is isomorphic to the image of F. So the proof follows more or less the same idea as we had we usually have with the isomorphism theorem with rings. And one should note also that all the results more or less that we have in rings all the results that we have with rings that are not depending on associativity extend also naturally to the n-ary case. So I chose only those two to illustrate. So, and the next step is talking about modules over n-ary algebras. So as we have with rings, n-ary algebras also can act on some vector space and in a given fashion and define what we call n-ary modules. So if I have an n-ary algebra, then an n-ary module over A is a vector space M together with n multilinear maps, which I denote M, J. Each one of them will go from n minus 1 copies of A times M to M. That is, it takes n minus 1 elements of A and one element of M and returns one element of M. We can also define equivalently an n-ary module as the direct sum A plus M together with an n-ary multiplication M extending the n-ary multiplication of A such that M of x1 to xn would be 0 whenever at least two of these elements are in M. So this corresponds to this in the sense that this allows me only to multiply sets with n minus 1 elements from A and one element from M. Here, if I take n elements from A, then the multiplication is what I have before in A. If I take n minus 1 elements of A and one element of M, then it's given by this Mj. And if I take more elements in M, which is not covered by this case, then here it would be simply 0. So now this definition is in the general case. What happens if we take a specific type of n-ary algebra, and how do we keep the properties of this? How is this going to be special in regards to n-ary modules? So just one thing before I move on is that this why do I have n multilinear maps here is because this algebra is not necessarily skew symmetric or symmetric, and each one of these correspond in here to the multiplication where the element of M, the unique element of M, is placed in a different position. So if I put the multiplication, the M element that I will act on at the last position or in the middle or the first position, the result will not be the same in general. So if we take AM to be an n-ary totally associative algebra, then an n-ary totally associative module over A is an n-ary module M such that A plus M, the direct sum with this extended product, would give a totally associative algebra. So as I explained just now, we have n different action maps because the algebra is not necessarily symmetric or skew-symmetric. However, in the setting of a symmetric or skew-symmetric algebra, it is sufficient to consider only one multilinear map of that sort. And if we take a n-ly algebra, then an n-ly module over A is an n-ary module such that the direct sum is an n-ly algebra. In that case, also in both of these cases, notice that M would be an ideal with the property that if I take the multiplication with more than 2 elements, then I would get not any element of the ideal, but exactly 0. This is also some, so to say, generalizing the idea of an abelian ideal in Lie algebras. So I will present also some 2 examples of n-ary modules for the cases of n-Lie algebra. So if I take the same space and the same multiplication, so as to generalize the adjoint action of a Lie algebra, then we get a n-Lie module over A. If I take another n-Lie algebra and then I have F, an algebra morphism from A to B, then I will define this L multilinear map as, if I take n minus 1 elements of A and 1 element of B, then what this would do is transform all the elements of A by F to elements of B, and then apply the bracket of B. And this way we also get an n-Lie module over A. So B would be an n-Lie module over A. And I will now move to the third point I wanted to talk about today, which is structure constants. Structure constants is simply put how I can represent in the most optimal way for computations the n-ary multiplication or an n-ary algebra in a finite dimensional setting. So let's take a finite dimensional n-ary algebra with dimension d and a basis ei of A. Since M is an n-linear map and there's not so much possibilities of structures of on a vector space of dimension n or d, then the only thing that changes that's important is the multiplication m. And the multiplication m is, since it is an n-linear map, can be represented by a family of dn plus 1 scalars. And these scalars are called the structure constants of A in this basis. So usually the notation is this, we have n indices below and 1 index above, so this is not a power. This family of structure constants represent m in the basis ei following this formula. So m of n different of n basis elements, ei1 to ein, is the linear combination of ek with these structure constants. So these indices below are represent which elements of the basis enter here, and this index k is simply which coordinate of this vector in this basis. So now that we can use these structure constants, why do we use them? All the identity defining various types of n-ary algebras, as well as several other properties that we can encounter, can be written as systems of either linear or polynomial equations, which is quite convenient for computational applications, so that we can either solve them, the equations, or study them using the tools that we have for polynomial equations. Can talk about the study of the algebraic variety of a given type of algebras of a given dimension, also over a given field. So now I will show how to get these equations, how this works. So first example that I will take is the number, or the Filipov identity. So I begin with this identity in this form. So only using elements of the basis, which is sufficient in this setting, because all the brackets or multiplications are multilinear. Then I substitute this bracket by this linear combination of structure constants, and do the same on the other the right hand side, taking care of using the right indices in each step. Then using multilinearity, I end up with this formula. Again, replace this bracket of basis element with a linear combination of this form. And then the next step is that, since these E are basis elements, then if those two are equal, then necessarily what happens is that these scalars are equal. So first I move this sum operator, the corresponding to this index, all out, and then what I have is that this is necessarily equal to this, and then I get this formula. So I would apply this for all indices that are free here. That is j1 to jn, i1 to in minus 1, and q. We can do also the same thing with the total associativity. So here we have another index coming to play. So here I have ki and kj, which are different from here, from this one to this one. So replace the inner multiplications by a linear combination of vector basis vectors and structure constants. Then multilinearity, that I get again here multiplications with only basis elements inside, so that I can again do the same operation. And the final result is this. So next I will show that also the homomorphism property or morphism property is also one of these properties that we can work with. So I will take here for simplification only a linear map on one algebra, an endomorphism, and then F is given by its matrix, which is the set of or the family of scalars Fij, such that we have this F of Ej is Fij Ei, the sum of Fij Ei. So these are exactly the columns of the matrix. So F is if F is an algebra morphism, then we have this. F preserves the products, and we can only work with basis elements. So what I do here is that I replace this with the linear combination of basis elements with structure constants, and here with the entries of the matrix of F. So what do I get is this F of this sum is equal to the brackets of all of these sums. And then using linearity in the case of F and multilinearity here, I take out all the sums and the scalars, get again F of one basis element so that I can apply this same here and bracket of basis elements here. So again, applying the same ideas here, of course, paying attention to indices and then reorganizing everything. And again, we have linear combinations of the same basis elements here, which are equal. So it means that the scalars are necessarily equal. And the end result is this. So notice that this one is a little bit less convenient to work with, but it's still a polynomial, since here we have n embedded sums, so as many as the n-ary of the algebra. So for ternary algebras, this is how those equations would look like. So the Filipov identity that I showed before, so this is Filipov identity. So here what happens is that instead of n different indices here, we end up with 3. And here the sum from 1 to n would be sum from 1 to 3. So I would have 3 of these. So this is the form it takes. And the morphism property here for n equal to 3, I only have 3 sums. So this number of sums is exactly the n-ary of the algebra here for that case. So for binary algebras, I would only have a double sum in here. And here, so for a ternary algebra, I have 3 embedded sums. So yeah, those can be in this form for a fixed d can can be very can be used for with computer algebra system, for example, some of the work that I also do. So that's all what I have for today. Thank you very much for coming.
Okay, thank you very much, Abdennour. This is
yes, it was quite short.
Quite short, but good presentation. And I guess there are some questions and comments, so everybody will be welcome to do this after I stop recording.